Right, thank you and good afternoon. So when we look at modern mammals, we find that they're easily distinguishable from other vertebrate groups, but also from their fossil ancestors by a number of characteristics, and those include, for example, the presence of fur, milk glands, a heterodont dentition, the trend towards an enlarged brain, and of course, famously, the secondary jaw joint formed between the dentary and the squamosal. And throughout the evolution from basal synapsids to modern mammals, we find that these and numerous further characters have been acquired in a stepwise fashion throughout the last 200 to 250 million years. And surprisingly for fossils, we find that throughout this evolutionary transition, that these character acquisition events are remarkably well documented in the fossil record, so that we have a fairly good idea of when and in which taxa these different characters first emerged. And obviously, as you can see here, by the sheer number of these different characters, these infer that we have here a tremendous change in the skeletal morphology. We have modifications of the cranial, but also of the postcranial skeleton. And in the cranial skeleton, this involves mostly a reduction in complexity and emergence of novel structures. So in the mandible, for example, we find a reduction in the complexity, a reduction to a single tooth-bearing bone. The postdentary bones are being reduced, finally detached and then incorporated into the mammalian middle ear. A novel jaw joint arises here from this structure, and similarly, we also find development of a secondary palate. So very, very strongly suggests that these different modifications have also functional implications, and for the last century, different hypotheses and assumptions have been put forward, mostly relating these modifications as a mechanism to decrease stress and to increase cranial stability. Mostly related, of course, in the cranial skeleton during feeding and mastication. But alongside these osteological transformations, we also find a rearrangement of the jaw musculature and other soft tissues, for example. And this rearrangement of the jaw muscles, for example, has often been seen as a mechanism to increase efficiency of the muscles and, as a result, of course, also of the bite force. And this reduced stress in the mandible, in particular in the jaw joint, then permitted the evolution of the secondary jaw joint. And also, these different assumptions and hypotheses have been tested qualitatively and quantitatively over the last century. None of these studies have actually exploited modern computational and digital reconstruction technologies. So the workflow we used here schematically highlighted. And similar to all the phylogenetic studies we've seen today, missing data and fossilization can represent and can induce severe problems for phylogenetic studies, but also here in biomechanical studies. So at the base, of course, of this workflow, we find the fossils, and fossils are obviously very problematic for biomechanical studies. Millions of years of fossilization have left their marks, deformation, distortion, fragmentation, all these kinds of artifacts we find in fossils. The further we go back, the more of those we find. However, we have the means with digital technologies to restore the fossils as completely as possible. And without going into much further detail here, just showing a few examples of what can be done with digital technologies, comparison between the original and the restored condition here for a few of these different Cynodonts and Mammaliaform taxa. And we used these three-dimensional digital reconstructions and restorations then all of those 6 taxa, which span the whole range, both temporally but also morphologically across the jaw joint transition. So we start with the primary jaw joint here with the cynodonts, and then via various transitional morphologies, we end up here with the secondary or mammalian jaw joint. And as a comparison for these 6 fossil taxa, we have the poster child for evolutionary studies on mammals, the opossum monodelphis here as an extant comparative taxon. So we used these 6 fossil taxa, the restored skulls of these fossil taxa, to reconstruct the soft tissues. Soft tissues, of course, here the jaw musculature. We did that with digital techniques as well. And again, I won't go into detail on this, just presenting a few key results here we found from the reconstruction of the jaw muscles. We find, for example, that the mammalian muscle division, so how the jaw muscle system is divided into different functional groups, is already in place in cynodonts in the same fashion as we find it in modern mammals. So preceding here the detachment of the primary jaw joint. Similarly, the mammalian muscle arrangement, so the way the different muscles attach to the bony correlates on the skull and lower jaw, is already in place, while we still have transitional phases here of the jaw joint. So both soft tissue characters, or both soft tissue character acquisition events, precede the osteological transformation here, which we find already completed in the soft tissues here in mammaliaforms, whereas with moving towards the crown group in mammals, the osteology lags behind these soft tissue developments. So we used both the osteological restorations and the soft tissue reconstructions to look at the function, doing this with, in this case, finite element analysis. I don't think I have to talk much about this technique, an engineering technique borrowed from engineering, obviously, which looks at stress and strain distribution due to loading. And we subjected all our 6 fossil taxa and the opossum to FEA and looked at the stress distribution first in the skulls. And we see a fairly homogeneous pattern here, at least for most of the cynodonts and mammaliaforms. Heterocodium, this taxon from the Jurassic of China, that comes out here as quite as an outlier, highly stressed both in the zygomatics and in the brain case. And I'll talk about that in a minute. If we look at that a bit more quantitatively and look at relative bite forces and relative muscle forces, we find that although the muscle volume decreases, the relative bite force more or less stays the same. So we have a fairly homogeneous pattern here regarding bite force at different tooth positions. If we look at that from a more modular perspective, given that different parts of the mammalian skull or the cynodont skull change in different respects, we looked at what are different modules, different regions in the skull are doing, so subdivided as shown here below. And from the basalmost taxa in this study to the modern taxa, we find again a fairly homogeneous pattern for all of these regions. Again, heterocodium falling out as an outlier here. A small trend we can observe is here in a slight increase in stress in the zygoma. This is not surprising given that the jaw muscles shift from the brain case as a good deal here towards the zygoma. The brain case actually shows a very, very slight decrease in stress. This is most likely not significant, but we see here kind of a trend in this. But overall, we see a fairly homogeneous pattern, as I said, not only for the complete skull, but also for the different skull regions. And the same we did for the lower jaws, and this time using both FEA and a kinematic simulation technique, multi-body dynamics, which allows not only the simulation and analysis of static models, but dynamic models. So we could record both bite forces, but also jaw joint reaction forces. That's what we were interested in. What was the jaw joint doing during this transition? If we first look at the FEA models, you can see this homogeneous pattern. Nothing really comes out here as specifically apart from heterocodium, again, this taxon. Jaw joint reaction forces trace the bite forces very, very closely. This is unexpected, so it has been hypothesized that with the shift in jaw joints that we might get the forces, so the resulting forces more towards the bite force. That's not what we're seeing here. If we look at this a bit more quantitatively, again, we see here the different stress patterns for different bite positions stay relatively the same. hydrocodium, again, this outlier. If we look at relative bite forces, those are mostly all over the place, so there's not a clear trend in any increase in efficiency or stress reduction. If we look at the jaw joint itself, again, we see there's no trend. So this is a bit surprising or not, depending how you want to look at that. So given most hypotheses over the last centuries speculated that would see an increase in efficiency, a reduction in stress with this transition of the jaw joints. It might be surprising, however, if we consider that optimization is not only considered in terms of increasing stability, reducing stresses, but also how perfectly adapted the taxon might be, given that we find several modifications in the cranial skeleton, of course, keeping the function to which this animal, this taxon, was adapted, keeping that function constant and upholding that function is also some kind of optimization, which we might be able to see here. What's happening with hydrocodium is hard to tell. One option might be that the muscle size in relation to the bone size, the skull size, the bone mass is very large, so we might get here very large bite forces and muscle forces in relation to the overall skull size. Another possibility is that this is some kind of an experimental morphology, given that we still have a very patchy fossil record for this part of mammalian evolution. This might just be an evolutionary dead end which did not evolve any further. And if morphology doesn't really play a role in the emergence of the novel jaw joint, and finally coming to the actual topic of my talk, or as is promised by the title, miniaturization might have to do something if morphology is not. And what we see throughout the Cynodont-Mammaliaform transition, we find that we have a steady decrease in size towards those transitional taxa, and then towards the crown group, again, a build up in size. So size might play a key role here, and we wanted to test that with different theoretical models. So we used the largest sizes recorded here in cynodonts and the smallest sizes, and then did a stepwise reduction in size between these models. With that, we got 7 different size stages, excuse me, and we tested again these different models, these different sized models for all the taxa we have in terms of tension and compressive stresses in the jaw joint. If we look at tensile stresses, we find that with the size reduction, we also, unsurprisingly, find a reduction in tensile stresses. Same for compressive stresses. The smaller taxa get, the less stressed, both compressive and tensile, is the jaw joint. However, of course, if we get smaller, if taxa get smaller, we also find a reduction in bite force. So the loss in bite force shown here as an opposite trend, and those taxa within the jaw joint transition range find they probably comprise some kind of compromise between maximally reduced compressive and tensile stresses and still retaining bite forces high enough to fulfill any feeding and mastication function. So to quickly sum that up, we find no evidence for any increase in cranial stability as often postulated in previous studies using these different biomechanical analysis techniques. Efficiency of muscle and bite forces is not supported in our study. However, miniaturization might play a key role here, as we've seen these two opposing trends of reducing stresses but also reducing bite forces and being then in this compromising range to fulfill jaw and feeding function might be a key factor here. We still find, as I mentioned, the retention of the cranial function despite a substantial modification and reorganization of the cranial skeleton, which is probably also one of the key issues here. We don't find any large-scale shifts in ecological niches or in habitats, so there's no real necessity to change function. Upholding function might be more important in terms of having a reorganization of the cranial skeleton. And briefly mentioned with Heterocodium, we see that there are some outliers, and those might just be functional and evolutionary dead ends. We don't have all the available fossils in this transitionary series yet, so these might easily represent some kind of experimental morphologies which did then not continue throughout. And with that, I thank you all for listening, and happy to take questions if we have any time left.